Hi, Isaac. Welcome to the podcast.
Hi, Robin. I'm very excited to be here.
It's a pleasure. Let's begin with where you work and what you do.
So I'm a machine learning research engineer at Roboflow, which basically means that I spend my time trying to build new types of models that our various users can use to better solve their different computer vision use cases.
All right. And we're here today because there's one particular model that you've been working on, RF-DETR. Do you mind telling us a bit about that?
Yeah. So RF-DETR is the new state of the art for real-time computer vision in terms of COCO, and it is the overall state of the art in for object detection as benchmarked by our data set that measures ability to transfer to downstream use cases, diverse downstream use cases, beating out uh, models that are orders of magnitude slower with
Right.
much bigger pre-training. Um, I say new not because it's just recently released, but in fact, the first version was released almost like 8 or 9 months ago now. But we're constantly improving it. We're constantly releasing new things on top of the model. And the model just a couple days ago was accepted to ICLR, which is a big step for us. And now it's a kind of an official peer-reviewed thing that is new,
Hmm.
which is cool.
Congratulations. So was your objective to make something that is, as you said, smaller, faster, and also a top performing model?
Yeah, we wanted to make something that people could use in a cheaply in a lot of different contexts without sacrificing accuracy. And specifically, we wanted to build something that just was going to work really, really well for people in a lot of different contexts,
Hmm.
data contexts as well as hardware contexts.
Of course, right. So how did you do it?
Um, so there are for the object detector, there are kind of two main things going on. One is we leverage kind of these or bigger pre-trained vision models, such as DINOv2. In our paper, we also talk about a bunch of other experiments we did with other foundation models, such as I think it was SIGLIP using SAM2 as a backbone, and also CAEV2. Um, but just to basically go in and have the model start knowing a lot about the world. So if your model knows a lot about the world to start with, then it needs less from you in order to understand what it is that you're talking about and what it is that you want to detect. Um, and then for the object detector, the other major aspect is most of these papers, um, well, I guess all of these papers um, use a fixed architecture. So they assume that there's one architecture that can work super super well in a variety of domains, and that's probably uh, true to a large extent. But if you're really really going for that high performance edge, in fact, there's no reason to assume that the kind of same neural architecture is going to work best for like many, many tiny objects distributed across like a high resolution image versus like maybe one object where you're just trying to figure out what class it belongs to. I mean, those, it seems rational to think that those would be different architectures would do better for those. Um, so the other major aspect with respect to object detection of the RF-DETR work was to introduce a neural architecture search method where we go in and we actually simultaneously train many thousands of different models, and then we can choose which architecture is the best for you
Mm.
uh, after. And we do this in a very very efficient way. So it only takes like 3 or 4 times the train budget to actually create a custom architecture for you.
Mm. So
And
just to make sure I understand, so actually when you do a training for RF-DETR, you're actually doing neural architecture search, is that right?
in the paper we do neural architecture search. We haven't released the neural architecture search engine to um, open source, but it'll be we intend for it to soon be a feature on platform.
Right, okay. So this is
So
specifically for use on the Roboflow platform.
yeah, our goal is to make it so that the RoboFlow open the RF-DETR open source is the best fixed architecture available. Um, Period. Including models that are orders of magnitude slower. Um, and but that you can do even better if you actually use the platform. So we can make some money from the thing.
Right. Okay. And but the public models, they also are the product of neural architecture search then.
Yeah, the public models are the result of neural architecture search against the COCO dataset. So
Okay.
the public models that do very well are applying RF-DETR neural architecture search to COCO. And in our benchmarks in the paper, we talk about what it is to apply RF-DETR neural architecture search to every single one of the 100 data sets that we use to judge downstream performance of object detectors.
Right. Okay. So it was quite a complex setup to run all these searches against well, 100 target data sets.
Yeah, we trained many, many thousands of models.
Mhm.
We feel like we actually we were very, very thorough about evaluating downstream performance of models in general. So for example, YOLO 26 dropped, I think last week or the week before. And like by the next day we had trained um every YOLO 26 size on R100VL, which is our data set from NeurIPS for this transfer. We had trained every YOLO 26 model on R100VL. So we had trained something like 500 neural nets overnight,
Hmm.
which may be more than Ultralytics trained when they actually um, w- within one day we may have become the largest trainer of YOLO 26 models, period, because we wanted to be very, very thorough about our analysis.
Right. Okay. And so what do we end up with? Do we end up with something that looks radically different from what is done in the past, or is it a very much a refinement?
You mean in terms of the types of networks that emerge from neural architecture
Right.
search?
Hmm.
Yeah, it's super interesting. Um, so we it's the same basic architecture as LW-DETR, um, but there's some kind of key differences. For example, well, there's some like kind of subtle structural differences. For example, like LW-DETR introduces this idea of like row major window detention in a VIT backbone, which is a mouthful, but it's kind of this just interesting memory optimization with respect to how to do window detention a little better. And they use four windows, and neural architecture search discovers that in most cases, the optimal is two. We find that we can actually, other DETR models use a fixed number of queries. So a DETR works by you encode your image with the backbone, and then you have queries that cross attend to the image hidden state. It's almost like an encoder decoder uh, transformer architecture in general, but you don't have the autoregression, and it's not pure transformers. You have some like convolutions and other stuff happening. But we find that we can actually drop queries after training to speed up inference, which is novel. I don't think any other papers talked about that. And what this does is it actually uh, encodes statistics as to how many objects are likely to be in an image um, from your specific data set. So we find that data sets with fewer objects or fewer objects per image after neural architecture search tend to prefer architectures that have far fewer queries, which gives you a meaningful speed up over
Mm.
architectures that only operate with a fixed number of queries. Um, we also yeah, there's a lot of fun stuff going on. We showed that RT-DETR showed that you could drop decoder layers. Modern DETR training, you have multiple layers in your decoder and you are simultaneously applying losses to every single one of the layers. So the idea is that each layer is acting as an iterative improvement as opposed to just optimizing such that the last layer representation is good. Um, RT-DETR showed that you could drop decoder layers and get nice performance. And we showed that in fact you could drop all of the decoder layers. So you're not even doing this like cross-attend part anymore. You just is just basically a ViT-forward pass.
Mm,
And that participates in it, which is a meaningful differentiation versus the rest of the field.
mm.
But yeah, and then we do other things in the paper. We also introduced a novel segmentation head architecture, which um, turned out to be very effective, especially when combined with neural architecture search. Um, I don't know if that answers your question. I kind of forgot what the question is.
Yeah, so have I, to be honest. But it's interesting that the neural architecture search is kind of steering you in maybe novel directions or
Hmm.
taking things to the extremes, which people just hadn't done themselves.
Yeah, I mean, it's interesting because like the way that you normally develop these models is you do just a massive amount of sweeps, like or a lot of papers will do a huge amount of sweeps. Um, and so finding these little details uh, for fixed architectures means meaningfully increasing your sweep size, which hugely increases the cost of running the experiment.
Mm,
But if you just kind of throw it into a neural engine, like a neural architecture search engine, it you don't do that. Like they're all trained at the same time. So your cost of developing these models is many orders of magnitude lower, which lets us pop out these kind of interesting objects that otherwise would not be found.
hmm So, how do you think this changes the approach people might need to take if they're working in specific domains like medical or
Mm.
satellite, where maybe the data just doesn't even look like anything that is being pre-trained on? And now you also have this option of, well, different architectures.
Yeah. Yeah, I think they're pretty complementary. Um, so one thing is that R100VL has different subcategories. So we've got like an aerial subcategory, we've got a medical subcategory, documents, a couple of them. And so we can do basically a differential analysis where we say how did different model families perform on different subcategories.
Sorry, just to
Um,
clarify, that's your data set.
yeah, sorry. RF100VL is our data set. We also open source NeurIPS 2025. SAM3 benchmarked on it, which was a nice validation for us.
Mm.
Like RF100VL is in table 2 of SAM3, which was actually a really nice moment. Um, yeah, so you can look at how does define do in aerial imagery, or how does like YOLO 11 do when you're looking at like flora and fauna.
Mm.
Um, and we find that RF-DETR does particularly well on medical and aerial and I think documents, if I'm remembering correctly. And these things that are more different from COCO and other standard pre-training data sets, such as like Objects 365. And the idea is that the DINOv2 backbone just has a lot of knowledge, and we're training in a way that we are attempting to be deliberate about minimally erasing that knowledge during our object detection pre-training.
Mhm.
So RF-DETR has a couple pre-training stages. One is the foundation model pre-training, um, which is not done by us, which is done by, in this case, Meta. And then we do object detection level pre-training, for which we use Objects 365. If for segmentation, we also used SAM2 to provide masks for every object in Object 365 and use that as pre-training for segmentation, which was an interesting thing,
Mm.
which helped. Um, and then we do COCO fine tunes. And in the NAS case, our neural architecture search is a weight sharing NAS. So we actually can pre-train all of the different subnetworks at the same time, so that we never actually make an architecture decision until like we've done our pre-training, we've done our fine-tuning on your data set, and then we do the architecture, which is kind of novel.
Mhm.
Um, but yeah, so we do a differential analysis and we find that we do well on data sets that are meaningfully different from kind of that standard COCO regime. And there are a couple interpretations of that. Like one is, as you said, like data being more likely to be in distribution as we do these large scale pre-trains. But there's another aspect, which is data may not be explicitly in distribution, but the features learned during a large scale pre-train may turn out to be more generic, meaning that they transfer better to out of distribution stuff.
Mm.
Um, and then there's some really interesting analysis on uh, man, there's so much cool stuff coming out about how to hold different um, visual pre-training strategies in terms of
Mm.
um, like the web SSL paper talking about how does DINOv2 strategy scale versus something like CLIP in terms of OCR recognition was like fascinating. Um, all this to say, you can have some unexpected. There's some evidence that some unexpected stuff can pop out as you start to reach certain scales.
Hmm.
Um, yeah. Does I hope that it was
Yeah, I mean,
relevant.
I think it's a really a novel area that I've not seen in the past, right? This kind of task-specific pre-training coupled with very large scale, steering us towards quite optimized architectures and potentially different pathways depending on what you actually want to do with the model.
Yeah. There's one major downside of this type of approach, which is actually why we invented the NAS stuff, or for RF-DETR's version of NAS, which is that people when they do these large scale trainings don't have us in mind. Uh, like they're not training these models with the idea that they're going to run on a Jetson Nano at high resolution, for example. They
Mhm.
tend to train basically larger models,
Mm.
and that's not great because if we want super low latency or alternatively really good cost efficiency,
Mm.
we have to figure out a way to work with those large models. Um, so, for example, the smallest uh, we spent a lot of time looking for basically just what is the smallest, highest performing pre-trained VIT we could find. Um, and we ended up with a couple options, including DINOv2 small. But LWDETR, which is again the paper that we started from, uses ViT tiny as their backbone for their small and nano models. So you've got I think it's like a 4x higher parameter count using the small than the tiny.
Mm.
And it's a slower model. So the question becomes, okay, how do you make use of like a 25 million parameter model on a nano time series? Like how do you get that to run as an object detector backbone in 2 milliseconds? And the turns out you can just kind of throw it into the neural architecture search engine, and it figures out, okay, well, actually, you can just run this at a lower resolution, and that works,
Mhm.
which is pretty convenient. Um, so we end up with like 30 million parameter models that are as fast as like 2 million parameter models from other families.
Mm.
Um, and one of the things that they tend to do is run at lower resolutions or use a larger patch size.
So I want to understand. So the optimization approach, is it good at finding smaller, more performant models, or can it also go the other way and say this is a bigger, higher performing model with other trade-offs?
It uh it can go both ways. We find the biggest gain from using NAS over fixed architecture so far in our experiments has been on these kind of like smaller things. But I
Mm.
don't think that's well, there's some interesting papers talking about scaling NAS methods. From my perspective, I think that's basically just because like the way we defined the search family has more options in this smaller range.
Right.
So I think we could run a larger search and presumably get higher
Yeah.
performance in that higher range as well.
Right.
And we also throw like some larger, we do a DINOv2 base backbone for the detector in the paper as well, which scales super well. And
Right.
we end up, that ends up being the first real-time object detector that claims to beat 60 map on COCO.
Hmm.
Whether or not you could actually get that with other approaches, like maybe no one published it before, but
Hmm.
to the best of my knowledge, this is the first published thing that is like, it's like 17 milliseconds at over 60 map, which is fun.
Hmm.
Um,
So the final result is basically a family of related models at different sizes with different sort of performances and requirements. Uh, Capabilities, you've got object detection, you said segmentation as well.
yeah, yeah, we built a novel segmentation head for real-time DETR models,
Mm.
kind of inspired by, well, based off the mask dyno approach, but they're using a hierarchical backbone and we're not, so we had to come up with some novel stuff there.
Mm.
Um, um, this is kind of a more mundane detail, but we did a lot of work on memory optimization at train time specifically. So the model, the new release that came out, I think last week for RF-DETR makes segmentation training like 3 to 4 times less memory intensive, but
Right.
for no change in performance, which
Oh,
is
okay.
fun.
That's
Yeah,
good.
like in fact the gradients are exactly the same. You just there's some tricks that make it so it just takes less compute, um,
Right.
which is really fun. I had a lot of fun building that.
Yeah. And then obviously
um,
reduces the cost of fine-tuning that model. You can use a smaller machine.
yeah, it takes it from like requiring 40 or 50 gigs VRAM to like 10, which is really cool.
Wonderful. So that's instant segmentation, is it?
Yeah, yeah.
Right. Okay.
Um, I'm we're looking at key points, and I would like to do semantic segmentation as well.
Hmm.
Um, from my perspective, we would like to be providing very, very, very high performance Apache 2 um, frameworks for kind of all these standard tasks.
Right. Yes. So similar to another framework that's not Apache 2.
Yes, very
Yeah.
similar and
Fantastic.
hopefully higher performance.
Yeah. Well, thank you so much. It's been really interesting technical deep dive. What's next then? I think you've hinted at a few things.
Yeah. So I it's um so you engage with the GitHub repo. Um and I am sure you noticed that we don't haven't really been super like I respond to issues, but I don't think many code changes happen that frequently.
Mm.
It, that's the big downside of being a research engineer. Like I don't really um write that much code. And the other people on my team, we're all I mean we're the the paper, we have 5 co-authors, uh, 3 of whom did like all of the training. Um, so very, very, very small team working on this.
Hmm.
Of course, we have wonderful, wonderful support, but ultimately there's a lot of work to do. So the thing that I'm looking forward to the most is we hired a new uh, um, open source research engineer, I think is his title, who's one of the key developers behind PyTorch Lightning.
Mm.
And the first thing that he's doing, and I don't know if you've
Oh,
noticed, but things are changing, and hopefully significantly for the better. Like we're actually getting a devoted dev time to making sure that that repo progresses in a nice
right.
way, which is super, super, super exciting. And I am you tagged me in an issue or I think a pull request this morning, and I'm planning on tagging him instead. I don't
Right.
know. We're figuring out how to work, like what the proper work dynamics are. But this is the first for me, like dealing with this large scale
Yeah.
of an open source project. So it's a massive learning experience, and I think it's I am interested in deferring to people who know more about how to do this than I do.
Yeah, yeah. So obviously a lot of attention for this model, performance, license, etc. Lots of people coming and creating feature requests, finding things that need addressing, and you've been heads down on the paper and version 2. So totally understandable that it's been hard to get to all those issues, and yeah, more hands on deck to address them. That's great to hear. So, and also you did mention that there's going to be an integration with the Roboflow platform itself. Do you mind talking a little bit more about that?
Yeah, I don't know how much I can say specifically, but we're planning on there's going to be a lot of performance improvements coming from a variety of directions in the next couple in the near future.
Hmm.
Um, One that I'm particularly excited about is a lot of these. Well, I think basically like all papers advertise like certain low latencies, including ours, that are not what you get out of the box. So we intended to be uh, kind of more reproducible in that we also released a benchmarking framework called single artifact benchmarking that attempts to make it so you could, okay, here's one file that contains everything about your model. It accepts an Onyx graph and it will give you the latency accuracy number. Like
Mm.
it just gives you the result and there's no subtlety about it. There's no caveats.
Mm.
Um, but the latency numbers we compute with that, and if you just run the RF-DETR repo, it just runs in pure PyTorch, and you don't get the same performance, which
Mm.
is kind of frustrating. Um, and that's basically true of like most research repos. It's true of most like open source things because the context in which you can do these optimizations, such as like TensorRT, is a little bit more sophisticated than is kind of easily pipelinable for a lot of a lot of users.
Mhm.
Um, so we there's a new uh, release people are working on within Roboflow to make our inference package uh, much faster, um, and that'll soon start to be able to actually. You should be able to just easily one liner get kind of the advertised performance not only on GPU but on a variety of other hardware providers. And I think
Right.
that's something that I think is really important. And I'm hoping that in the open source repo, we can basically take that same ease to work with infrastructure and um, make that kind of the happy path for researchers who would like to translate their work into some high performance artifact for downstream consumers.
Right.
That's a
So
goal.
really
I think that's
closing
a
that loop so people know the performance they can get if they put this into a real world system and building all the infrastructure to enable the use of it. Well, that's really great to hear. Obviously, it's on GitHub. We'll put the link in the show notes. I know that there's a Roboflow newsletter. People can get updates. If they want to hear more updates. Is that the best place to go, or is there another platform as well?
yeah. The newsletter is I think good. We're also hoping to be more active in the Git repo. So if you would like to engage, I mean, I answer technical questions if you have them in that repo all the time. Hopefully that will be more uh, popping in the near future.
Right.
Um, yeah, the,
Brilliant. Okay,
I'm
so
very excited.
GitHub is the place, and
Yeah, newsletter, GitHub. Yeah, I think
fantastic.
yeah. I'm pumped. I think there's a lot of um I think you have to have kind of a base model that you care about
Mm.
as a platform, and then you can start making sure all the infrastructure pipelines in ways that are
Yeah.
really respecting that model. And I think we're working on it, and I'm excited for the result.
Well, it's a really fantastic outcome. Looking forward to seeing how it progresses. Once again, thank you for joining me today, and until next time, take care.
Thank you, and take care as well.